Alright guys, problem number 36. A laser beam with a wavelength of 524 nanometers is exactly perpendicular to a screen having two narrow slits spaced 0.150 millimeters apart. The interference fringes, including a central maximum, are observed on a viewing screen 1 meter away. The direction of the laser beam is then slowly rotated by 1 degree about an axis parallel to the slits until it makes an 89-degree angle with the screen. How far does the central maximum move from the viewing screen? Alright, so this one is just a little bit confusing, but I think it's pretty straightforward if we draw a sketch. So if we look at the top view of our setup, looking down on the grating, here we have our two slits, and we have rays incident from a laser which is perpendicular to the slits. So the initial rays or initial waves are incident perpendicular to the slit, so this guy is 90 degrees. And when those waves spread out on the other side, if we call this wave 1 and this wave 2, the path length difference between 1 and 2 is given, if this is our angle theta here, is given by this piece right here, and if this is the spacing between the slits d, then the length of this path length difference is d times the sine of theta. All right, now what happens is it says that the laser beam is rotated by 1 degree around an axis parallel to the slits. So if we imagine an axis coming straight out of the page, we are rotating the laser, okay? So the laser is going to rotate this way, okay? And we're just rotated by just 1 degree, okay? So let's go ahead and draw that picture. So this is the initial picture. All right, and then the picture after rotation, once again the top view. Now our laser has been rotated so that it has an angle of incidence phi. And now this angle is no longer 90 degrees, it's 89 degrees, and our angle phi is 1 degree. I've drawn an exaggerated angle here just so we can see what happens. And then these once again head off towards their maxima. They spread on the other side of the slits and head out and create an interference pattern on the screen. And this we will still call our angle theta. And this is wave 1 and this is wave 2. So we've just taken our laser, which was perpendicular to slits, and we've rotated it 1 degree up, okay? And we've included this angle phi. Now the path length difference between wave 1 and wave 2 is this piece, which is still d times the sine of theta, and now this piece right here, which is d times the sine of phi. So our total path length difference between wave 1 and wave 2 is d times the sine of theta plus d times the sine of phi, right? And we're asking for the location of the central minimum. So in that case, we want the difference in the path length between these two. Typically, we set this equal to m times lambda, but in this case, m is equal to 0 because we want the central maximum. Okay. In other words, we want to know when delta r, or the path length difference between wave 1 and wave 2, is 0. Right? So we can factor out a d. And that's all equal to 0, and the d cancels. Okay, so this condition is going to be met then when the sine of theta is equal to minus the sine of phi. Okay, and this is what defines our angle theta. So our angle theta then for the central maximum, which is when, once again, the path length difference between wave 1 and wave 2 is 0, is going to be equal to the sine inverse of the sine, excuse me, minus the sine of phi. All right, so now we just need to figure out what the actual coordinate of that is going to be. And our coordinate for our maximum, y sub m, is equal to L times the tangent of theta sub m, right? This just comes from ordinary geometry here. If this is our angle theta, and this is the distance L between the screen and the slits, then this piece here, which is going to be the coordinate of that maximum, is L times the tangent of theta. So we can just plug in our value for theta here. We're going to get that y sub 0 is equal to L times the tangent of the sine inverse of the minus sine of phi. And we can plug in some numbers, and this is going to be, how far away is it? 1 meter. L is 1.0 meters times the tangent of the sine inverse of minus the sine of 1 degree. And this gives us a coordinate for our position of the central maximum of 1.75 centimeters. And notice in this particular case that it does not depend on the split spacing d, but instead just the angle of incidence phi that the laser is incident on the slits on the left-hand side.